Alright, from today on, we're going to have a look at a new chapter, Chapter 5, Energy Changes and Rates of Reaction. And today, let's have a look at the first lesson of Chapter 5, Energy Changes in Chemical and Nuclear Reactions. Our ability to harness energy has contributed greatly to the development of human civilization. For most of human history, the only way to transport people and things over land was by walking or through animal labor. Then, during the Industrial Revolution of the 19th century, inventors found ways to harness thermal energy to do work. Energy released by burning coal was used to heat water, releasing steam fast enough to move mechanical parts in machines. People and goods could then be moved long distances by steam-powered locomotives and boats. The next advance took place in the late 19th century in the form of internal combustion engine, which produces energy by burning gasoline. Today, there are more than 500 million vehicles that are powered by the internal combustion engine, which is shown here in Figure 1. As this number grows, the demand for inexpensive and reliable sources of fuel also increases. Most of these vehicles use fossil fuels, which are non-renewable and negatively affect the environment. How will we meet our energy needs for transportation and other activities in more sustainable ways? To answer this challenge, we need to understand the energy changes that take place in chemical and nuclear reactions. So first, let's have a look at the nature of energy. The study of energy changes during physical or chemical changes in matter is called thermochemistry. The study of thermochemistry uses some familiar terms in very precise ways. Scientists define energy as the ability to do work, and work is energy transferred to an object by a force that causes the object to move. For example, the energy to lift satellites into orbit comes from simple chemical reactions that release huge quantities of thermal energy. The hot expanding gases released during the rocket launch do work on the rocket by pushing it into the sky. However, no work is done if the force of the gases is inadequate to get the rocket off the ground. Both energy and work are measured in joules, which is abbreviated in the letter J. That's the unit of energy and work. All forms of energy can be classified as either kinetic energy or potential energy. Potential energy is energy due to the position or composition of an object. Kinetic energy is energy of motion. For example, the water behind a dam has a great deal of potential energy because of its elevation. This energy can be used to do work on the blades of turbines in a hydroelectric generating station. As the water falls, the potential energy is transformed into kinetic energy. The falling water causes the turbine blades to spin. The kinetic energy of the spinning turbines is transferred to a generator and transformed into electrical energy, another form of potential energy. The energy associated with chemical bonds is also potential energy. Chemical bonds are the result of attractive forces between the nucleus of one atom or ion and the negative charges of electrons in the other atom or ion. The amount of energy released or absorbed in a chemical reaction equals the difference between the potential energy of the bonds in the reactants and the potential energy of the bonds in the products. For example, energy is released during the combustion of gasoline because the products has less potential energy than the reactants. In an internal combustion engine, the products of this combustion reaction are hot gases. The molecules in the hot gases that are produced by the engine move much faster than the molecules in the incoming cool air. Therefore, the combustion gases have more kinetic energy. This energy is used to do work on the mechanical parts inside the engine and eventually make the car move. And there are some other trivial concepts in this lesson. So next, let's have a look at thermal energy, heat, and temperature. Be careful with the difference between each of these terms. The total quantity of potential energy and kinetic energy of a substance is called thermal energy. In general, the quantity of thermal energy of substance depends on how fast its entities, namely atoms, ions, molecules, or polyatomic ions, are moving. When a substance absorbs thermal energy, its entities move at a greater speed, and the substance warms up. When a substance releases thermal energy to its surroundings, its entities move more slowly. And again, these entities are atoms, ions, molecules, or polyatomic ions. And then the substance cools. In science, heat is a verb that refers to the transfer of thermal energy from a warm object to a cool object. So when we heat water in a kettle on a stove, we transfer thermal energy from the burner to the kettle to the water. Similarly, when an object cools, it transfers thermal energy to its surroundings. Next, the term temperature is a measure of the average kinetic energy of the entities in a substance. As a substance is warmed, some of its particles move faster. The average kinetic energy of the substance's entities increases, and so does the temperature of the substance. For example, a cup of hot water has a higher temperature than an iceberg. The average water molecule in the hot water has more kinetic energy than the average water molecule in the iceberg. However, we should notice that an iceberg contains billions more water molecules than a cup of hot water, right? Therefore, the total quantity of thermal energy of an iceberg is greater than that of a cup of hot water. Are you clear? Okay, next, let's introduce the law of conservation of energy. One important characteristic of energy is that it is always conserved. We cannot create new energy, nor can we destroy energy by using it. Energy can only be converted from one form into another. Think about the combustion of a propane in a barbecue. Chemical energy stored in the propane is converted into thermal energy and light energy. However, the total amount of energy before and after the combustion reaction occurs remains constant. These ideas are summarized in the law of conservation of energy, which states that energy cannot be created or destroyed. To help analyze energy conversions involving chemical reactions, chemists find it useful to divide the universe into two parts: the chemical system and its surroundings. A chemical system is composed of the reactants and products being studied, and the surroundings are all the matter that is not part of the system. In the propane gas barbecue, for example, the chemical system is composed of reactants, which is propane gas, C3H8, and oxygen gas, O2, and the products, which is carbon dioxide gas, CO2, and water vapor, H2O. The surroundings include the barbecue and the food on the grill. Chemical systems can be classified as being open or closed, which is shown here in this figure. An open system can exchange both energy and matter with its surroundings. An operating propane barbecue is an example of an open system. Propane gas flows into the burner and thermal energy and products of combustion flows out. A chemical reaction that produces a gas in a solution in an unsealed beaker is also an open system, which is shown here on the left side of this figure. Since energy and matter can flow into or out of the system to the surroundings. The surroundings include the beaker and air around the beaker. Whereas a closed system can exchange energy but not matter with its surroundings. A glow stick is another example of a closed system. Light energy released when chemicals inside the stick are mixed flows out into the surroundings. However, the matter, that is the chemicals, remain sealed inside. And besides these two systems, there's another kind of system exists, which is called an isolated system. In an isolated system, neither matter nor energy can move into or out of the system, which is shown here on the right side of this figure. However, it's impossible to set up a true isolated system on Earth. And there are two types of reactions in terms of the direction of the flow of the energy, which are called endothermic and exothermic reactions. First, let's have a look at exothermic reactions. During a chemical reaction, the chemical bonds in the reactants are broken, and new bonds are formed to produce the products. The potential energy of the entities in a stable structure, such as the atoms in a molecule or the ions in the ionic compounds, is lower than the potential energy of the individual isolated atoms. Therefore, bond breaking requires energy, while bond formation releases energy. From the law of conservation of energy, we know that the total energy in a chemical system and its surroundings must be the same before and after a chemical reaction occurs. If more energy is released from the formation of new bonds in the products than is required to break bonds in the reactants, then the chemical reaction will release some energy to the surroundings, right? A chemical reaction system that releases energy to the surroundings is called exothermic. So the prefix EXO here means out of. The products of a exothermic reaction have lower potential energy and stronger bonds on average than the reactants. For example, the combustion of methane is an exothermic reaction. The balanced chemical equation for this reaction is given on the top right. And notice that an energy term is included on the product side of the equation to show that the energy is actually released. This energy is the difference between the energy absorbed by breaking bonds in the reactants and energy released by forming bonds in the products. The quantity of this energy is the difference in potential energy between the reactants and the products and has a symbol delta EP. Since the combustion of methane is exothermic, energy is released to the surroundings, mainly as thermal energy and light energy. And here, figure 4 illustrates the changes that occur during this reaction in an open system. The quantity of matter in this system, represented by the tan box, remains the same. And released energy, which is a large arrow, flows to the ground surroundings, which is denoted by the yellow area. When an exothermic reaction releases thermal energy, the temperature of the surroundings increases. A reaction that absorbs thermal energy from its surroundings is endothermic. The prefix here, ENDO, means inside. During an endothermic reaction, the chemical system absorbs energy from the surroundings and increases its potential energy. This means that the products have higher potential energy and weaker bonds on average than the reactants. The synthesis of nitric oxide from its elements is an example of an endothermic reaction, which is represented by the equation shown on the top right. Notice that for an endothermic reaction, the energy term is included on the reactant side of the equation. Figure 5 here illustrates the changes that occur during this reaction in an open system. The quantity of matter in the system again remains the same, but now energy flows from the surroundings to the system. Alright, next let's have a look at nuclear energy. Unlike chemical reactions, all nuclear reactions are exothermic. Per unit of mass, nuclear reactions release much more energy than exothermic chemical reactions. Two nuclear reactions involving large quantities of energy are fission and fusion. A fusion reaction occurs when nuclei of a small atomic mass combine to form larger, heavier nuclei. Fusion reactions are responsible for the release of vast amounts of energy in stars, including the Sun, which is shown here in Figure 6. The Sun consists of 73% of hydrogen, 26% of helium, and 1% of other elements. Hydrogen nuclei under immensely high pressure in the Sun undergo fusion and form helium nuclei. The fusion process releases energy, some of which reaches Earth. The fusion of hydrogen atoms produces 1.7 times 10 to the power of 9 kJ or kilojoules of energy for each mole of helium produced. So we could review the nuclear notation a little bit here. An element with a chemical symbol X is represented as S with the subscripts A and Z, where A is a mass number of the protons plus number of neutrons, and Z is atomic number, which is number of protons, right? And the neutron is subatomic entity, and symbol N10 is used to show that neutron has a mass number of 1 and atomic number of 0. So using nuclear notation, the equation for the fusion reaction of hydrogen atoms could be written in the formula shown on the bottom. Scientists have worked for decades to find a way to develop fusion reactors to generate energy, but the intense pressure and heat needed for fusion to occur have made this difficult to achieve to date. Hopefully we can have a breakthrough in the near future. During fission, large nuclei with high atomic mass are split into smaller, lighter nuclei by collisions with a neutron. The nuclei of all elements above atomic number 83 are unstable and can undergo fission. Fission does not normally occur in nature. Fission reactions produce vast quantities of energy. That is, millions of times more than is released in chemical reactions, which is shown here. Nuclear power plants use the fission of uranium-235 to produce electricity. When a neutron collides with a uranium-235 nucleus, the uranium nucleus splits into smaller nuclei and releases energy and additional neutrons. These neutrons collide with more uranium nuclei, causing these nuclei to split and release more energy and even more neutrons. So the equation for the fission of uranium is shown here on the top left. Uranium is used in nuclear power plants because it undergoes a fission chain reaction. About 15% of all electrical energy in Canada now is produced by the fission of uranium in nuclear power plants. Nuclear power plants can generate much more electricity from a small amount of fuel than can power plants that use fossil fuels. For example, uranium fission can produce about 26 million times more energy than the combustion of equal mass of methane. So, energy changes occur during any physical, chemical, or nuclear change. Here, Table 1 gives an example of each of these types of energy changes and the magnitude of the potential energy change in the system. So have a look at this table by yourself. Notice that the potential energy change varies considerably